Hello everyone and welcome back. Today we're going to talk about Angular Kinematics, or also known as Rotational Kinematics. But before we begin, I want to make sure to point out that in my last video, we derived these three equations, and it is very important that you watch that video first. Otherwise, you're going to be pretty lost when I start doing derivations in this video. Once again, this is arc length, which very commonly in physics equations is going to essentially be displacement. I'll explain why later. This is therefore angular displacement. This is tangential or linear velocity, angular velocity, tangential or linear acceleration, and angular acceleration. And these three equations are the only equations that can translate between linear and angular. In other words, if you have a problem that's going between one and the other, one of these three equations must be used at some point. That is why they are so important. So we're actually going to begin with a chart. And as I make my rotational videos, I'm going to keep bringing this chart back because a reoccurring theme you are going to see is that for most of the topics we are going to discuss, there's going to be a clear connection between linear and rotational. And I'm going to show you a big one right now. For starters, you have linear displacement. Units are meters. Well, the rotational equivalent is angular displacement. Units are radians. Again, if you'd like to see the connection between the two, make sure you watch my last video, which was titled Intro to Angular Physics. We have linear velocity, which had the units meters per second. We had angular velocity, which had the units radians per second. We had linear acceleration, which had the units meters per second squared. Again, linear acceleration is the most important variable in linear physics. We have angular acceleration, which had the units radians per second squared. And unsurprisingly, is the most important variable in angular physics. Okay, I'm going to jump right to an equation that came up last time as well. One of the first equations that came up in this entire video series was average velocity, which was displacement over time. And in our last video, angular velocity, average, is simply angular displacement over time. A small note while I'm here, one of the reasons why I'm being careful is by the time this screen is done, you are definitely going to want to screen capture it, because this screen is going to end up having the translation between every linear and any rotational equation in the course. All right, next up, I'm going to place our four kinematic equations, the equations that we literally derived way back in our earlier videos. And here they are, the four kinematic equations. I'm going to start with this one, which is pretty much our average velocity equation. Again, the 1/2 VI plus VF here is just average velocity if you go from one velocity to another. Case in point, here are my two average velocity equations. If you take them and equal to each other, you will get this equation right here. Now, I'm not going to bother with full derivations because watch this. I have displacement. Angular version, I have angular displacement. 1/2, I have velocity initial plus velocity final. I have angular velocity initial plus angular velocity final, and time has no rotational equivalent. This is my acceleration equation. Acceleration is change in velocity over time. So I have angular acceleration, Vf minus Vi, omega f minus omega I, over time. Third kinematic equation, displacement. So angular displacement, Vi times time, omega I times time, plus 1/2 at squared, 1/2 alpha t squared. Fourth and most powerful kinematic equation, Vf squared, omega f squared, equals Vi squared, omega I squared, plus 2a delta x, plus 2 alpha delta theta. Ta-da! Here are the four angular kinematic equations. Done. You literally just need to translate the linear to the rotational variables, and that's it. Believe it or not, that is most of what we're going to be doing when we deal with rotational. This is actually why I prefer to teach rotational last, because it actually helps a lot when reviewing earlier material because it is practically the same. The only real big difference right now is instead of meters, you're dealing with radians. There's really only going to be 2.5 topics that are entirely new, but we'll deal with that when we come to it. For now, I'm going to take these equations and put them on the side here so they're not in the way. So these are our translation equations, and on the bottom there are going to be our angular kinematics equations. All right, let's actually do a problem. So to start out, a bicycle tire has a diameter of 0.7 meters and is currently moving at 12 meters a second. So here's my bicycle, and it is moving to the right at 12 meters a second. First question, what is the angular velocity of the tire? Well, let's start as we always do by listing givens. For one, they give us that diameter. I'm going to immediately transfer that to radius, which is 0.35 meters because we don't use diameter. It is currently moving at 12 meters a second. That is velocity initial, 12 meters per second. What is the angular velocity of the tire? Well, that's omega. It's right here. And we were pretty much just handed both things we need. So omega, I'm going to divide by r, 12 meters per second, over 0.35 meters. Meters cancels, and you get 34.3. Now notice meters cancels is technically 1/seconds, but the actual unit is radians per second because you divided by the radius. Because again, radians is essentially a fake unit. It does not actually exist. And once again, I explain why in my Intro to Angular video. Let's ditch the bike. 2. If the tire slows to 10 radians per second in 6 seconds, what is the angular displacement? So first up, we have some new givens. The tire slows to 10 radians per second. Radians per second is angular. And since it slows to 10 radians per second, this is final, which of course makes our earlier one initial because we used initial velocity here. 10 radians a second. And we're given time, 6 seconds. Angular displacement. Now I'm going to mention this. Of all the new terms, this is the one students tend to forget. If displacement is delta x, angular displacement is delta theta. In other words, how many radians did the object move through as it spun? Now it's just a game of which equation can we use? I have omega initial, I have omega final, I have time, which pretty clearly speaks to this one right here. 1/2 omega initial plus omega final times time, 34.3 radians per second plus 10 radians a second times 6 seconds. Gives us 132.9 radians. All right, next question, I'm going to jump over to the right because now we're going linear. How far did the bike go? So they're literally asking how far did it travel, which means we need delta x. So I'm going to pause here and give a reminder. Every time the wheel turns, the bike moves forward. And if the bike tire moves one rotation, that means the distance the car traveled would be equal to one circumference of the tire. In other words, imagine the tire is a roll of toilet paper. If you allow the roll to move for one full rotation, you'll have a length of toilet paper that's equal to the circumference of the roll of toilet paper. If I was to take this length and wrap it around the tire, that would essentially be delta S. So if this bike is moving forward, delta S and delta X are the same length. And that is why I could literally do this. Even though arc length is technically wrapped around the tire, if I laid it out in a straight line, I would have displacement, which means I can get displacement simply by doing theta times r. 132.9 radians times 0.35 meters gets me 46.5 meters. So in short, we just went from rotation of the tire to how far the bike actually went. Let's keep going. 4. What's a tire's angular acceleration? Again, was important concept in the course. If acceleration is the change in velocity over time, then angular acceleration is the change in angular velocity over time, or this equation right here. And I don't need to list any more givens because we already have them. Alpha is omega final minus omega initial over time, 10 radians per second, minus 34.3 radians per second, over 6 seconds, gets me negative 4.05 radians per second over seconds, which is radians per second squared. A quick mental check. The original angular velocity I had already set as positive right here. The tire slows to an angular velocity that is right here, which means I should be expecting a negative acceleration here. In other words, the idea is identical to linear. If the direction of the acceleration is opposite the direction of the velocity, then the velocity will decrease. If the direction of the acceleration is in the same direction as the velocity, then the angular velocity would have increased. Okay, last question. What is the bike's acceleration? Now, I have two choices here. I could use our old acceleration equation. We do have the translation equation to velocity, And I could use angular initial and angular final and radius to get those velocities. However, since we have angular acceleration, we are going to do a shortcut. The tangential or linear acceleration is the acceleration of the bike, which is simply alpha times r. Negative 4.05 radians per second squared times 0.35 meters. When you multiply these, meters jumps on top, radians is just gone because, again, it was never there in the first place, which gives me a linear acceleration of negative 1.42 meters per second squared. And as a quick check, this bike was moving to the right and was decreasing in velocity. It slows down. So if velocity is to the right and acceleration is to the left, the bike should slow down, which means we should get a negative acceleration, which we did. So there's something I want you to notice here. As long as you are able to identify the givens in the situation, the difficulty has not increased at all. I recognize when I have linear variables. I recognize when I'm going to rotational. I recognize when I'm using rotational. I recognize when I could jump from linear to rotational pretty easily. If you notice, I kept all the rotational over here, and when I was going to linear, I kept them over here. You don't have to do it like this, but you should have some way of keeping it organized. Once again, recognizing your givens is the most difficult and most important step in the process. Notice when I got a new variable, I very clearly defined for myself that I found it. Another good idea would be to simply add them to your givens list as you find them. But in short, Angular Kinematics is really no different mathematically than linear kinematics. It's simply an understanding of visualizing the rotation of the object. In this case, that was the bike tire as it's going down the road. The only thing that was really new is being able to translate between linear and angular, which is just the proper use of these two equations in the upper right-hand corner. The perfect example was this last part of the question, where this translation formula provided a very quick shortcut to the linear acceleration. All right, so two last things. One, again, here are the linear to angular equations. They are very important to know. Two, here are angular kinematics equations. But the list that is probably going to be most useful to you is going to be this one. Linear, rotational, or angular. Our next topic is actually going to be a new one, but then we're going to jump right back to this list and just keep it going. Okay, I'm going to end it here. Have a good day. This is Mr. M, signing off.